Swayam Prabha. Digital India. Educated India.
Welcome to the course on micromachining. Today I am going to talk to you regarding advanced micromachining methods, one of them being abrasive jet micromachining. It is a mechanical type of advanced micromachining process. What we are going to discuss in this particular lecture are as follows. I will give brief introduction to the abrasive jet micromachining process. Then we will discuss the process parameters of abrasive jet micromachining, then mechanism of material removal in abrasive jet micromachining, what are the different types of micro patterns that have been fabricated by some of the researchers will be presented to you. Then important is the masking technology. When we are talking of abrasive jet micromachining, this masking technology becomes very important, and what are the various ways of preparing the masking, what are the various ways of feeding the abrasive particles, etc. We will discuss this. So, that will come under abrasive powder feeding techniques. Then there are certain applications of this particular process, I will talk about them. Then what are the advantages and disadvantages of this particular process, we will see them, and I will try to solve one of the example based on the theory of abrasive jet micromachining process. Now, I will like to acknowledge the abrasive jet micromachining chapter 5 written by Professor T.J. Ko of South Korea in the book on Introduction to Micromachining, published by Narasha Publishing House, New Delhi. And also I will like to acknowledge the help and the lecture delivered by Dr. Professor AJMM from IIT Kharagpur on abrasive jet micromachining in the course on micro manufacturing that was held at IIT Kanpur. Now, abrasive jet micromachining is a relatively new approach to the fabrication of microstructures and creation of micro features in macro and micro structures or devices. Abrasive jet micromachining is a promising technique to three-dimensional machining of glass and silicon in order to realize economically viable micro electromechanical system, that is known as MEMS. I will also like to emphasize before I proceed further that in this particular process there is no constraint that workpiece material should be electrically conducting or non-conducting, magnetic or non-magnetic, or high high thermal conductivity or low thermal conductivity. No such constraints are there for using this particular process. It implies a mixture of fluid with abrasive particles, and air or a specific gas is used as a fluid in which abrasive particles are mixed. We will see details of all this. In contrast to direct blasting of the abrasives, the surface is exposed completely to the erosive action of the particle beam, so that you can create the desired features on different devices or the components. Hence, before processing, the substrate material has to be partially shielded by applying an erosion resistant mask. We will see the details of different types of the masks that are used in abrasive jet micromachining, how to prepare them and so on. Only where the mask does not protect the workpiece, material removal will take place. So, wherever we want to remove the material from the workpiece, that part or that area has to be naked, means it should not have any mask on it, and then the jet of abrasive particles will hit that particular area and remove the material. This method is used for making accurate shallow holes or grooves, and with the use of mask, patterns on the target material can be created. Now, the resulting erosion of target material can be controlled using masks and by varying parameters such as impact angle and particle flux density, velocity and particle properties. All of them will affect the performance of the process, accuracy of the features that you are creating, tolerances on the features and so on. In contrast to conventional microfabrication methods such as wet and dry etching, all these methods we will discuss later on, abrasive jet micromachining is capable of machining anisotropic patterns and suspended structures with high erosion rate and relatively low cost. This process is comparatively low cost process as compared to other processes, as you will appreciate when we deal with details of this particular process. Globally, it introduces the concept of precision machining techniques to conventional blasting through the use of fine and hard abrasive particles. This is very important. Particle size should be fine because it is going to control the shape and size of the features you are creating. And second thing is hard abrasive particles, as I have mentioned in my introductory lectures of the micromachining processes. Abrasive particle hardness should be much higher than the workpiece material hardness, otherwise it will not give the desired results. And constant powder feeding devices, what are the various feeding devices we will discuss later on, and the masking technology, all of them are going to affect the performance and the quality of the products being produced. Advantages of abrasive jet machining or abrasive jet micromachining process are low cost of capital investment and operating cost is also low. Environmentally friendly process, it is called as environmentally friendly process, means it is not going to affect the environment surrounding to the equipment of the abrasive jet micromachining process. No major health hazards are there, and ability to machine anisotropic and suspended structures on the same substrate. Now, however, it is always desirable that you surround and the equipment where you are machining the material with the help of abrasive jet micromachining process, because very fine abrasive particle may get suspended in the environment, which will be harmful for the operator or the people standing around this particular setup. In addition, multiple depth features can be machined on the same substrate. Unlike chemical etching where the entire substrate is etched at a constant rate. This simply means that at different locations you can have different machining rate to create the multiple depth features by this particular process. It is typical. AJMM applications include drilling, cutting and engraving of glass, ceramics and some hard materials. You can call that different kind of the operations can be performed by this process, because drilling, cutting etc. are different kind of operation using the process of abrasive jet micromachining. It can also be used to etch labels in plastics, metals. Deburring is a very important application of this particular process. Deflash and clean materials after conventional machining. During conventional machining, the material has burrs, flash etc. deposited or remaining on the surface that has been machined. So, all that can be cleaned using this particular process. However, the process parameters are different for cleaning as compared to the process parameters used for material removal. Schematic diagram, as you can see here, this is the abrasive jet micromachining which has created the different features, or you can call it as abrasive jet machining process also. The basic difference between the two is that in abrasive jet macromachining, your feature size is always larger than 1 millimeter, while in case of micromachining your feature size is considered to be less than 1 millimeter. At least one dimension of the feature should be less than 1 millimeter, then only it can come under the category of micromachining. And you can clearly see different features created here with the help of abrasive jet micromachining. This is the nozzle through which abrasive jet, means the air containing abrasive particles or any other gas containing abrasive particles, beam is there which is hitting the workpiece surface and creating different features. Different parts of this particular system are as follows. Here you can have gas supply, you can have N2 gas or other type of the gas that we will discuss, or you can have the air inside this particular cylinder. Then you have the filter. Before sending it further, it has to be filtered, cleaned here, and here is the pressure gauge and pressure regulator which will tell you at what pressure the gas is there or air is there. Then you have powder supply and mixture is there in this particular one, and you have the vibrator. Vibrator is very important, it plays very important role, because mixing of the very fine abrasive particles with the air is done with the help of the vibrator. Then you have foot control valve. You can operate it with your foot so that you can control the amount of the gas going to the nozzle for removing the material from the workpiece by abrasive jet. This is the abrasive jet, this is the nozzle, this is the workpiece, and here the material is being removed by this particular abrasive jet, and this feature is being created with the help of this. As I mentioned little earlier, that all these abrasive particles should not be allowed to get suspended in the environment, so that you have the hood over here you can see, and through this yellow color hood you send or exit these this used air or the gas, and some of the maybe abrasive particles also may go out through the exhaust hood. Now, good and important drawing here, you can see this is the distance between the bottom face of the nozzle and the surface being machined. Here this is the surface being machined in the beginning. So, it is called as nozzle tip distance, abbreviated as NTD, or stand off distance, that is written as SOD. So, you can call it as SOD or NTD, and this is very important, as we will see that as this SOD keeps on increasing, the shape of this abrasive air jet keeps on changing, and that will affect the shape and size being machined on the workpiece. Here is the workpiece, and this is the nozzle diameter around 0.3 to 0.5 millimeter, that you can call as 300 to 500 micrometer. Now, you can see the enlarged view of this particular area that is shown over here. Here abrasive particle is hitting the workpiece surface, and abrasive particle is much harder than the workpiece surface. So, it is creating this kind of the cavity. Now, whether it is a ductile workpiece material or a brittle workpiece material, depending upon that the mechanism of material removal are different. So, if it is a brittle material, it will create the crack over here and remove the material from here. As you can see, this is the material that has been removed from here. So, this kind of the cavity is being produced on the workpiece surface. Now, so this tells you the mechanism of material removal, and this jet consists of air or any other gas plus abrasive particles. Now, important thing to note here is that the velocity of this jet is around 300 to 500 meter per second, depending upon the requirement of the process, and which depends upon the workpiece material properties and abrasive particle properties. Then you have the flaring jet of the jet. Now, as I will show you later on, that in the next slide also, as this extent of distance increases, the jet gets flared off. That means the size of the cavity will keep changing as you change the extent of distance, and for accurate machining you should keep very low extent of distance. For the case of macro machining, I am talking about macro, not micro, that time you can keep around 1 millimeter as the extent of distance if you really want very accurate cavity to be machined. If it is micro machining, then the extent of distance should be much lower than 1 millimeter itself, and due to the flaring the cavity dimensions changes. With the changes NTD, nozzle tip distance or extent of distance. Abrasive particles repeatedly hit on the workpiece surface and create the cavity. Brittle fracture separates out tiny particles or worn out particles to produce a cavity. As you can see over here, this cavity is produced, and brittle fracture, this material is being removed from this cavity. Cavity width is always equal to or greater than the nozzle inner diameter. As you can see, this is the nozzle and this is the inner diameter of the nozzle. So, the cavity dimensions will be equal to or greater than this nozzle diameter, and when it is equal to, it will be only when you have the very small extent of distance, otherwise it will be bigger than the inner diameter of the nozzle. Cavity depth depends on workpiece feed rate, abrasive particles mass or density and pressure, because feed rate, particle mass or density and pressure, they are going to affect the energy with which the abrasive particles are hitting the workpiece, and for how long time they are in contact with the workpiece surface will be decided by the feed rate. That is why all these three parameters are going to govern the characteristics of the machine cavity. Now, let us see another schematic diagram of the abrasive jet micromachining setup. Now, before I tell about this, you can see here air gas abrasive particles, they are coming through this particular bottom part of the nozzle, and this is the tip of the or inner diameter of the nozzle at the bottom face, and this is the workpiece. They are coming and hitting the workpiece surface and creating the cavity over there, and this distance is extent of distance. What I am trying to tell here is that you have to be careful in deciding the extent of distance. Suppose your jet is hitting over here and this is the bottom part, then this is the extent of distance. But if this jet has created a cavity like this and your jet is hitting over here, then really standoff distance becomes this, not really this. So, you have to be careful in deciding what is the standoff distance going to be. Then let us see, again compressor is there, which will raise the pressure of the air or the gas that you are going to use. This is the relief valve over here, this is the cylinder where you are collecting the air or the gas, and this is the drainage for this particular whatever is left over there, you can drain out before really refilling the cylinder. You have the air filter cum dryer. Drying of the air is very important, otherwise it will not give you proper performance as you expect. So, you have the filter for cleaning the air or the gas and drying it, both functions are performed over here. Then you have the pressure gauge. So, you can see at what pressure you are having the air or the gas over here, and you can change that with the help of the compressor. Then opening valve, the extent you open this particular valve, you can let the air or the gas go inside this chamber, and pressure regulator is there. With the help of this pressure regulator, you can control the pressure of the air which is going inside this particular chamber. In this chamber, you are mixing the air with the very fine abrasive particles, and they get mixed up over here, and that is why its name is given as mixing chamber. Now, proper mixing for a definite period is very important, so that whatever air abrasive mixture is going through this particular pipe to the nozzle, it is homogeneous in nature, that is desirable, so that when it comes out of this nozzle at the bottom, it will hit the workpiece surface. So, you can see here, because top surface, this surface is to be machined over here, that is why you can see this is the standoff distance. If jet has already penetrated the surface at the inside this workpiece, then your standoff distance is going to change. So, you can see that standoff distance is continuously changing. So, if you cannot move the nozzle nearer to this particular workpiece, then standoff distance continuously keep changing, and instead of straight sided cavity, you will get the tapered cavity, and that is what is the characteristic of this particular process, because the standoff distance is only in terms of few hundred micrometer in case of micromachining, and if your nozzle cannot move into that, then definitely standoff distance is going to increase and you are going to get tapered cavity. Now, let us discuss principle of abrasive jet micromachining. In this process, fine microabrasive particles are accelerated in a gas stream, commonly air at a few times atmospheric pressure, but in place of air one can use other neutral gases also, just like nitrogen or other gases. The particles are directed towards the focus of machining less than 1 millimeter from the tip, that is known as standoff distance or nozzle tip distance. As the particle impacts the surface, it causes a small fracture, and the gas stream carries both the abrasive particles and the fracture wear particles, as I showed in the earlier slide, that abrasive particle as well as burn out particle both moved away from the surface of the workpiece. As you can see here also, that abrasive particles, they are coming with the air. So, they are forming abrasive air jet, and as you can see here, this abrasive particle is hitting the workpiece surface and removing the material, and the size of this cavity formed, as you can see, is slightly bigger than the diameter of the nozzle at the bottom surface, and this is 0.8 is approximately the nozzle tip distance or standoff distance. The velocity here can be around 150 to 300 meter per second, and tip is made up of very hard material, that is tungsten carbide or jam or any other material, because abrasive particles are continuously hitting the bottom part of the nozzle, and this also wears out, and once its wear is beyond a certain limit, then it should be replaced, otherwise you will not get the accurate workpiece surface, and this workpiece work is written over here. Now, you can clearly see, as I mentioned in the introductory part, the abrasive particle may hit the workpiece at normal angle, that is 90 degree, or at an angle other than 90 degree. Now, if it is hitting at an angle other than 90 degree, you can see this is the abrasive particle, initial velocity is there, and it penetrates because of the normal force component which is acting on this abrasive particle, and it shears the workpiece material depending upon the depth of penetration by the shearing force or component of the force in the this particular direction, and this is the chip being produced, and this chip depends upon the depth of penetration of the abrasive particles. It may be of micron size, it can be of nano size also, and you can see this is the depth of cut because of the penetration of this particular abrasive particle. So, this shows you the mechanism of material removal. For ductile material like aluminum or work hardening due to repeated deformation, then cracking may take place. If the abrasive particle is hitting the ductile material at around normal angle and continuously hitting the abrasive particle, will make this ductile material work harden, and once it work hardens, then it becomes a kind of brittle material, and then brittle fracture will take place over there. So, the angle with which abrasive particle is hitting the workpiece surface makes a lot of difference as long as mechanism is concerned, and this model was proposed by Finney long back for as the cutting wear. So, similar to material removal in milling or grinding will take place, for ductile material cutting wear is also in evidence. Process parameters of abrasive jet machining. The abrasive is one of the important parameter of abrasive jet machining. Composition of the abrasive particle, strength of the abrasive particle, size of the abrasive particle, and mass flow rate, all of them are going to affect the process performance. Here, strength of the abrasive particle, I will like to mention that if abrasive particle is not much harder than the workpiece material, then abrasive particle itself will get fractured or broken out into smaller pieces, and it will not be able to perform any cutting action. So, before selecting the abrasive particles, you have to be very careful that its hardness is much larger than the workpiece material. Second thing, the gas. The composition of the gas is again important. The pressure at which the gas is going to the nozzle and hitting the workpiece surface will make a lot of difference, because that is going to decide what is going to be the kinetic energy of the abrasive particle while hitting the workpiece surface. So, larger the pressure, larger will be the kinetic energy, and vice versa. And then the temperature of the gas also makes a difference, because gas or air temperature is high or low, then its own properties will change, and that will affect the air abrasive jet characteristics and the velocity with which the abrasive particle is going to hit the workpiece surface. That is also very important, and this velocity is the function of the pressure at which you are exiting the gas or the air out of the nozzle. Then the nozzle, geometry of the nozzle is going to decide what kind of cavity you are going to get. If nozzle is circular in shape, you are going to get the cavity made circular, or if it is a rectangular shape or triangular in shape, whatever is the shape of the nozzle tip, that shape will be replicated on the workpiece surface. The material of the nozzle is again important, because nozzle will be wearing out, or wear of the nozzle will continuously take place, because abrasive particles are first rubbing the nozzle surface while coming out of the nozzle. And then stand off distance, SOD, or nozzle tip distance, that is another parameter which is going to considerably change or affect the cavity characteristics that you are going to machine. Then the feed rate will decide how deep is the penetration of the abrasive particles inside the workpiece. Smaller the feed rate, deeper will be the cavity that you are forming, or larger the feed rate, then shallow will be the cavity, or less depth will be the of that particular cavity. And another very important parameter is inclination angle to the normal to the workpiece surface. That makes a lot of difference, as we saw just in the earlier slide. And if it is 0 degree, that is normal to the workpiece surface is 0, that means abrasive particle is hitting at 90 degree, and rather than deforming the material, it will be hardening the material by work hardening process, as I mentioned few minutes back, and then the material removal will take place by brittle fracture rather than deformation process. Then abrasive particles, the choice of abrasive particles depends on the type of machining operation. Now be careful about the process and the operation. Here cutting is the process, but operations can be like drilling operation, milling operation, or even turning kind of the operation. So these are the operations, but mechanism of material removal will be the same. The abrasive particles should have a sharp and irregular shape for better performance. So because that is going to affect the performance, so normally it is desirable that abrasive particles are irregular in shape and sharp, fine enough to remain suspended in the carrier gas, as we have seen that the mixture of the carrier gas and the abrasive particles from the chamber is going to the nozzle. So if they are fine, you will get better homogeneous mixing of abrasive particles and the gas. If they are not fine, means they are larger in size, then many of them may remain suspended, but some of them will remain at the bottom of the container or the chamber, and you will not get right kind of abrasive flow rate and proper machining. It should have excellent flow characteristics, so that narrow and fine areas are reachable to them. If they are not fine, in the fine areas they may not reach, because here we are talking about the micro machining. So definitely the size of the abrasive particles should be very, very small, or even if you can find in nano size, it will be still better, so that they can reach in the fine areas, a very small areas where machining is required. Some of the abrasive particles are like this: alumina Al2O3, it is not very hard material, hence it is used mainly for cleaning purposes, some soft material cutting purposes also, and deburring is very important work or phenomena that is done with the help of this particular abrasive particles. Then silicon carbide is comparatively harder, and you have the applications like cleaning, cutting, deburring, etc., as in case of Al2O3, but for harder workpiece materials, because this is harder, so workpiece material can also be harder, and you can perform these kind of the operation. Then you have the glass beads, which are very soft compared to other abrasive particles, and this is used for creating matte finish on the workpiece surface. And then you have sodium bicarbonate, again used for cleaning, cutting and deburring of soft material. So, the thing that you have to take care of is that the abrasive particles should be chosen, so that their hardness is much larger than the workpiece material hardness. Then carrier gas, there are certain characteristics of the carrier gas, very important. One has to be careful that the carrier gas should be non-toxic in nature, it should be cheap and easily available. First characteristic is very important, otherwise it will harm the people standing surrounding to your work area. It must not flare excessively when discharged from the nozzle. Flaring is a very big problem in case of abrasive jet machining, we will see few minutes later, because when the jet is coming out, it flares out like this, and some gases flare out more compared to others, and if flaring is more, then the cavity, instead of getting the cavity like this, you will get the cavity like this, and in many cases you may have to reject the workpiece with this kind of cavity if your requirement is this cavity. All this will depend upon what tolerances you are getting in the cavity and what is permitted for the requirement of that particular cavity. Commonly used gases are CO2, nitrogen and air. Now, depending upon the cost and your work, you can choose one of them. Air is mostly preferred due to universal availability at no cost, because from the environment you can fill it in the cylinder, compress it with the help of the compressor to get the desired pressure of the air, and very important thing is that is it is non-toxic in nature, because we keep breathing every day 24 hours. So, it is not harmful to the human being. Now, nozzle materials are again important parameters, because as I mentioned few minutes back that abrasive particles are in contact with the nozzle inside the hole, in the hole. So, it keeps on wearing continuously, and if it is not very hard, then it will change its shape and size, and you will not get the correct kind of cavity. And just like so, flow rate of the air or the air abrasive jet is quite high, as I have already mentioned, it may be as high as 300 to 500 meter per second. So, supersonic air flow velocity in the nozzle is there. Homogeneous dispersion of abrasive particles over the width is always desirable of the nozzle, so that you get proper cutting. Then you have long lifetime of nozzle, otherwise if wears out quickly, then you have to replace the nozzle, and it always costs something to the user. It has to withstand the erosive action of abrasive particles, and materials for nozzle are like tungsten carbide and sapphire. Both are very expensive, so one should use the nozzles very carefully. Now, effect of the feed rate, like medium feed rate, now you can see here, when low feed rate is there, medium feed rate is there, high feed rate is there. So, depending upon the feed rate, the characteristics of the surface being machined are obtained here. Normally high feed rate is there, you are not able to cut it properly, and you can see the striations are there or cavities are formed, and then high peaks are there. Here they are less because you have the medium feed rate, but when you have the low feed rate, then such kind of irregularities are not obtained here. So, depending upon your requirement, how good surface finish you need and what kind of accuracy you need, you have to choose whether it should be low feed rate, medium feed rate or high feed rate. So, which feed rate is better, it will be decided based on your requirement of the component. Now, as I was telling you earlier, stand-off distance is very important, stand-off distance or nozzle tip distance, and it is going to govern the quality of the features being produced by abrasive jet micromachining. Now you can see here that as the stand-off distance is increasing, flaring is increasing. Here it is very good at low stand-off distance. As you can see here, if it is 0.75 stand-off distance, then this cavity obtained over here is very close to what you really want, because nozzle tip distance is very small. But as the nozzle tip distance is increasing, as you can see here it is 1 millimeter, then the shape and size of the cavity has changed. It has expanded at the top, and if you further increase to 1.5 millimeter or 2 millimeter, you can clearly see the characteristics of this cavity have completely changed as compared to the first cavity when you had the 0.75 millimeter. So, depending upon your requirements, you can select the nozzle tip distance or stand-off distance. So, a decrease in stand-off distance improves accuracy, decreases kerf width and reduces taper in the machine groove. You can see here, this is the good accuracy obtained, and this is known as, say here 0.73 or 0.7 millimeter is known as kerf width, or 0.5 is the kerf width, or 1 millimeter is the kerf width, 1.5 millimeter is the kerf width. So, as stand-off distance is increasing, kerf width is increasing. Now, it reduces the taper. If in this particular case you can see very small or almost no taper is there, but as stand-off distance is increasing, this is the taper angle. So, the taper is continuously increasing. Here taper is less, but it increases as stand-off distance is increasing. So, stand-off distance, control of stand-off distance is very important for the quality of the part being machined or the feature being machined. So, what is kerf? That I have just shown to you. What is the kerf width? Which stand-off distance is more accurate? Normally it is recommended 0.5 millimeter or 0.75 millimeter, but 1 millimeter becomes quite large, because as you can see over here that taper is increasing and kerf width is also increasing. So, I can also say that depending upon the accuracy you want in the feature being machined, you should decide the kerf width. Then abrasive flow rate is another important parameter. MRR increases only up to a certain value of abrasive flow rate, beyond which it starts decreasing, because if stand-off distance if flow rate is increasing, then abrasives coming in the flow rate are also increasing. So, they per unit time they are increasing and MRR keeps on increasing, but if flow rate is very high, then it is claimed that it starts decreasing the material removal rate. We will see the details of this. As abrasive flow rate increases, the number of abrasive particles cutting the material also increases, thereby increasing the material removal rate. It is very obvious that larger the jet is coming per unit time, more abrasives will be there and more amount of material will be removed up to a certain limit. And then you have, after a certain value of abrasive flow rate, abrasive flow velocity decreases to the extent that it results in reduction in MRR. Now, because abrasive flow rate is very important also, because if it is large number of abrasives and pressure remains the same, then jet velocity will also decrease. In the case of ductile materials, material is removed by plastic deformation and cutting wear, or plastic strain and deformation wear. Now, during impact, when the yield strength of the material is locally exceeded, plastic deformation takes place in the vicinity of the impact. We have already seen in the earlier slide that when the angle of the inclination of the abrasive particle is different from the is greater than 0, this is the angle of incident, then it is going to go, this abrasive particle will have two components, one is the normal force, another is the shearing force. Depending upon the magnitude of the normal force, it will penetrate inside the workpiece surface, and depending upon the shear force, it will be removing the chip, removing the material in the form of the chip. So, plastic deformation is going to take place in the vicinity wherever the impact is taking place, because when this penetrates inside, it is going to remove the material in the form of the chip like this, and this chip will come over here and you will get the removal of the material. After multiple impacts, a plastically deformed surface layer may form near the eroded surface, and therefore, the yield strength of the material increases due to strain hardening. What I am telling here is that in place of hitting at an angle, if the abrasive particle is hitting at an angle of 0 degree from the normal to the workpiece surface, then it will keep hitting it again and again rather than shearing the material, and strain hardening will take place, and the workpiece material hardness in this particular zone will increase, and it will become brittle material. And then still if it continues hitting the workpiece surface, when it becomes brittle material, then brittle fracture will take place and material will be removed in the form of the micro nano chips. So, upon further deformation, the yield strength at the surface of the material will eventually become equal to its fracture strength, and no further plastic deformation will take place. Rather than at this point, the material surface becomes brittle and its fragments may be removed by subsequent impacts. This will result in micro nano brittle fracture, and the material will be removed in the form of the chip. So, mechanism of material removal for brittle fracture: during brittle erosion process, particle impact produces different types of cracks and chipping with negligible plastic deformation, as we will see. In the case of brittle materials, it may take place due to indentation rupture, elastic plastic deformation, critical plastic strain. So, let us see, indentation rupture may take place or elastic plastic deformation may take place. In elastic deformation, whatever deformation is taking place, it is recovered once the force is removed, but in plastic deformation, when force is removed, the deformation persists over there. In critical plastic strain theory has been applied for analyzing the mechanism of material removal. Radial cracking and propagation or surface energy criteria can be seen over there. Let us understand the theory of mass loss of workpiece material during abrasive jet micromachining or abrasive jet machining. The mass loss of workpiece is proportional to the amount of abrasive particle mass. You can see here K rho m v square over h. So, this will give you the related to the kinetic energy. K is greater than normally 2, it is a constant, is a dimensionless factor. M and v amount and velocity of particles, this will give you the mass of the abrasive particle, this is the velocity of the abrasive particle, rho is the density of the abrasive particle, and h are density hardness of the workpiece material, hardness of the eroded workpiece material, eroded material or workpiece material respectively. The above relation is true for brittle erosion, but not for softer materials. That means, hard materials which are removing the material by brittle fracture, for that this particular formula is applicable. Due to time variant erosion behavior, especially at normal impact angle, particles tend to embed in the material, resulting in an initial gain in weight of the specimen. Now, after this incubation time, steady state erosion is established and mass loss from the eroded material is proportional to the amount of abrasive particles, because number of the abrasive particles, more amount of the material will be removed from the workpiece. The principal empirical relation between the erosion rate is expressed as follows, that is erosion rate, and it is proportional to K, velocity coefficient K commonly reported for material between 2.3 and 3, for glasses 2 and 4, and for elastomers it is 1.8 to 3.2. So, depending upon this you can calculate mass loss in AJMM process. Now, here machining of PMMA and glass, you can see here AJMM can machine much steeper side walls and flatter bottom section in PMMA than those in glass. As we will see the figures here, for PMMA there is only a small probability of a particle rebounding from the steep side wall and hitting the opposite side. In addition, it is likely that particles lose more energy at first strike in PMMA than in glass, causing less damage during the second strike. So, you can say the cross sectional profile of typical masked PMMA channel, after one pass you will get the profile like this, which is quite shallow and wide, but after 11 passes you will get this proper profile. So, as the number of passes increase, the depth of the profile or the feature you are creating keeps on increasing, and cross section of 250 micro channel machined in borofloat glass after 11 passes. So, this is for the glass, this is for the PMMA, and this is for in the glass after 11 passes you are going to get this kind of the profile, while after 11 passes in PMMA you are going to get the profile. So, you can understand that based on the characteristics or the properties of the workpiece material, the profile features are also changing, because it is a kind of triangular shape that you have got, while it is a kind of near to rectangular shape that you have been able to machine. So, all this will depend upon the material, workpiece material properties as well as abrasive particles properties, and this paper has been taken from this particular reference, as you can see over here, published in the journal Wear. Now, here quickly let us see the effect of different abrasive particles type and workpiece material. The appearance of the dimples during AJM for 10 seconds, they have been machined for 10 seconds under different conditions for various machining sets of abrasive and ceramic. Let us try to understand this. Here you can see these are the workpiece material like ZRO2, silicon nitride and alumina and silicon carbide, while these are the abrasive particles SD, GC and WA. Here you can see WA means aluminum oxide, GC means silicon carbide, ST means synthetic diamond. Now, you can clearly see that at different same conditions remain, but the workpiece material is changing from zircon oxide, Si3N4, alumina and silicon carbide. So, you can see the different cavities that have been formed, their dimensions, diameter is different and depth is completely different, and the surface finish that you have obtained in all the 4 cases are different. However, abrasive remains the same. Same way, when abrasive changes, material, workpiece material remains the same. You can see that depth is different, cleanliness with which this cavity is being formed is also different. Here you can see the depth has very minimal, but here again depth increase in case of silicon carbide. So, depending upon the type of the abrasive particles, as you can see in the last case, all the 4 have got almost good depth of penetration, except in this particular case, that is alumina. So, it clearly indicates that depending upon the type of the abrasive particles and type of the workpiece material, you are getting different cavities or different shape and size of the cavities. Same thing has been expressed here in terms of material removal rate. As you can see here, workpiece material ZRO2, you can see along this particular arrow, the material removal rate is different in all the 3 cases of Z particles. This is for WA, this is for GC, and this is for SD. So, again in case of Si3N4, different material removal rates are obtained with different abrasive particles. Same is true for Al2O3 and SiC. In SiC, you can see in case of SD, very high material removal rate is there, while in case of WA, very small material removal rate is there. So, you can clearly see that the type of the abrasive particles and type of the workpiece material will decide what is going to be the material removal rate. I will stop here. Thank you very much.